So let's provide an overview of Lab 3, which is density and specific gravity. I would highly recommend that you reference the examples that we covered in the notes on the water displacement method and how to measure the density of liquids. The notes were explicitly designed and set up for this lab. So in this lab, you're going to calculate the density and specific gravity of a substance. So the required reading, you're going to need to read the introduction and procedure page for experiment 3. So let me show that. So if you have your lab manual handy and we pull open our lab manual, you're going to be looking at experiment 3, which is density and specific gravity. It should start in around page 23 of your lab manual. Is everyone able to find this lab in their lab manual? Does this look familiar to everyone? Good, perfect. So I have some introduction sections available. You're welcome to read it. It's very similar to that of your lab manual and your note for density. Just to provide you some really critical components, just as review, density is the mass of a sample over the volume. Typically, we measure mass in units of grams, and the volume has units of milliliters. Now, when you're measuring volume, just as a refresher, you measure from the bottom of the meniscus at eye level. Just like other graduated devices, you read graduated volumetric devices in the exact same manner. You can report your certain digits, those explicitly marked by a tick mark, as well as one additional digit as your estimated digit. Typically, mass is calculated by difference. So you weigh the mass of an empty beaker, you add your liquid to the beaker, and then to calculate the mass of your liquid, you subtract the mass of your liquid and the beaker by the mass of the empty beaker. Okay. So further information on density is found in part A of your lab manual. For specific gravity is very easy. So specific gravity is the comparison of the density of your liquid with the density of pure water, which is 1 gram per milliliter. So specific gravity is defined as the density of a substance over the density of pure water, which is 1. Specific gravity has no units. So specific gravity of 1.5, for example, is a valid measurement. Specific gravity is unitless, has no written units. Does that make sense to everyone? Does that make sense? So, part B, that's essentially it. You just divide the density by 1 and you report your specific gravity with no units. For part C, for the density of solids, to calculate the density of a solid, you need the mass and volume. The mass we can get from a balance, and the volume of a solid object can either be calculated using the formula method or more commonly the water displacement method. This is the method that we'll be utilizing a lot this session. So the object is placed into the cylinder and then the new volume is read. So we record the initial volume of water, we record the volume of the water and our object, and by difference, when you subtract the final volume from your initial volume, you're able to calculate the volume of the object. This works because objects will displace water equal to their volume. Now, what's really cool about this is by measuring the density of a solid, if it's a pure substance, and for many pure substances, density at a given temperature and pressure is a fixed quantity, and we can use our measured density to assign the identity of our substance. So By measuring the density of an unknown solid and then comparing the density to the density values of known materials, we can assign the identity of our unknown solid. So you can tell me whether or not the solid samples that we measure are copper, aluminum, lead, etc. The water displacement method was covered in our chapter 1 notes, and we did 3 examples using that method. Does this water displacement look familiar to everyone? Does this look like something that we've seen before? Perfect. And I would highly recommend looking back over your chapter 1 notes for additional sample calculations for water displacement. So in part D, what you're going to do is you're going to generate a graph of mass as a function of volume. So because density is independent of the size or amount of a substance, what we're going to do is we're going to measure the density of a metal by looking at the mass and volume of a different number of metal pieces. So what we're going to do is we're going to collect the mass and volume data for our metal pieces, and then we're going to plot, and we're going to generate a plot of mass of metal pieces versus the volume. And the slope of our plot will provide us with the exact density of our metal sample. I provided some guidelines for drawing graphs. So this is a sample graph that I've made in Excel. For this experiment, there's a graph in your lab manual. There's a piece of graph paper that you'll be using. And I'd like you to generate your graph in Excel. So key things, you need to have a title with what variables are being studied, in this case, mass and volume. The axes should be labeled with the variable and the units. And then you're going to want to make sure that your graph data points occupy around 70% of the graph. You mark your data points with dots, and then what you're going to do is you're going to draw a best fit line that gets as close to as many data points as possible. Now, once you have your line, you can calculate the slope by selecting 2 points on the line. So you're from this line, you're going to read off an X and Y value for 2 points on the line. And then what you're going to do, slope is the difference can be defined as rise over run, which is the difference in the y-axis values over the difference in the x-axis values. And in this case, the slope is the difference in the 2 mass values for the 2 points on your line divided by the difference in the volume values on your line. And by taking the rise over run, by calculating the slope, you'll get the density of your sample. If you use Excel to plot your line, the M value, the number in front of the X, will be your slope. You're going to want a graph in the lab book, and we'll talk about that momentarily. So that's an overview of the laboratory itself. The data that you've been provided is shown here. So for part A, the density of liquids, I provided you all of the data in these pictures that you would need to calculate. In this case, for part A1, I have all the data that you need for you to calculate the density of water. So you're going to measure the mass of water and the volume of water. Does it make sense what we're doing? So for part A1, does it make sense that each of the pictures I provided you, gives you enough information to fill in the blanks in your laboratory manual. Does that make sense to everyone? So you're gonna view the pictures and then you're gonna fill in your lab manual with the measurements. So for example, for part A2, when you're dealing with an unknown liquid, we go to part A2 and I have all the data provided for you to complete part A2. And there's a title above each picture that tells you what you're seeing in this picture. For part C, for the density of solids, one thing to note, rather than a single piece of metal, I've used a collection of pennies as your solid. And here's the data showcasing the initial volume and the volume of solid. So from each of these pictures, you'll be able to collect your data for part C, the density of solids. For part D, you're going to record the volume and mass over 4 trials. The solid in this, so you're going to record the volume over 3 to 4 trials. So, for example, we're going to add 4 different portions of our metal pieces. You're going to record the mass and volume of the metal pieces for each of the trials. And note, and this is really important, you need to calculate the total mass of metal pieces in the graduated cylinder for each step of the 4 trials. So let me show you what I mean. Let me show you what I mean, and let me show you how your data is going to look. One moment. So let me open up a new page.
I have a problem.
Yes, how can I address your question?
I had purchased my lab manual, but it actually the report is actually, it got teared apart, got ripped. So then I can just copy and paste what you have on here and submit it that way.
So you need to submit organized data tables identical to the lab manual. This lab manual is the copy I have that we're just viewing, just so that way you can correlate to the lab manual that you currently have in your possession. What I would recommend is finding the lab manual data tables and getting a sense of what parameters are required for your data tables from a partner in your class. And then you can turn in the data tables with all of the data in the lab manual with properly formatted data tables, just like in your lab manual. Does that make sense?
Yes, thank you.
Perfect. So just to explain a little bit further what we're doing in part D. So just to start off with, we have 4 groups of metal pieces. We'll title them 1, 2, 3, and 4. And we have a graduated cylinder that contains water. So for trial 1, for trial number 1, this is lab number 3. It's called density and specific gravity, and it should be on around page 21 of your lab manual. Okay, so this is specific for part D. So first things first, we're going to record our initial volume of water. Okay, so we have that data in hand. We're then going to add our first solid. We're going to add our first portion of solid. So after trial 1, we'd have measured the mass of our first portion of solid, and we have added it to our graduated cylinder. The water level will rise, and then what we're going to do is we're going to calculate the V final, the final volume of water after trial number 1. So we have the mass of our solid, and we can calculate the volume of our solid by taking V final minus V initial. Okay? This will be our first data point. So for trial number 1, we're going to have the mass of our solid and the volume of our solid. Okay? Does that make sense so far? Does this first part make sense?
Yeah, we have so we find the first initial volume that's given to us in the pictures.
Yep, exactly.
Okay.
And
we already have the math for the number 1 for the we're given.
I'll actually talk about that in a moment. So to calculate the mass of the solid, you're going to measure the mass of a beaker. That's what you see in the picture. And then I also have showed you in a separate picture the mass of the sample 1 plus the beaker. And so you can calculate the mass of sample 1 by taking the mass of the sample 1 plus the beaker minus the mass of the beaker. And you'll get this data from the photos. Does that make sense?
Yes, thank you.
Perfect. So now we're going to repeat the exact same process for trial number 2, except the only thing that's going to change, so for trial 2, we're going to record the mass of our solid, except this time, the mass for trial 2 is equal to the mass of solid 1 plus the mass of solid 2. Because when we add our second metal piece to our graduated cylinder, we now have both pieces in our graduated cylinder. In this case, we're then going to record the final volume of water for trial number 2. And in this case, the volume of our solid total is going to be equal to V final for trial number 2 minus our V initial from all the way up here. So we're calculating the total mass and the total volume of our solid. So we'll have the mass of solid total and the volume of our solid total. Does that make sense to everyone? Does everyone understand this critical distinction? Does everyone see how if we have both of our metal pieces in our graduated cylinder, we need to add both of the masses together? Does that make sense to everyone?
No, I didn't understand the math part of it.
Ah, okay.
For the trial 2.
Okay, so we can measure the mass of our solid, right? So in the first trial, we just measured the mass of solid 1. We put it in the graduated cylinder. So the mass in our graduated cylinder is just the mass of our solid 1, right?
Right.
And now for the second part, we can measure the mass of solid 2 by putting it in a beaker and then adding our solid 2 to it. So we can get the mass of solid 2, just like we did the mass of solid 1. Now, the critical distinction is when I add solid 2 to my graduated cylinder, what is in my graduated cylinder now? Is it just solid 2 or do I have solid 1 in there as well? Looking at the picture.
Solid 1 is in there also.
Yep, exactly right. So in order to measure the density of both of these pieces, I need to calculate my total mass by adding up the mass of solid 1 and solid 2. Does that make sense?
Yes, I have to go back and look at the pictures. I don't have it right now in front of me.
It's okay. But look, just from the picture that I've shared right here, do you see how both solid 1 and 2 have been added into our graduated cylinder?
Yes, yes, I do.
And so then in order to figure out the mass of sample in our graduated cylinder, we add the mass of solid 1 to the mass of solid 2.
Yes, makes sense. Thank you.
And then to calculate the volume, you take the volume final, which is the final volume of water and solid in your graduated cylinder, and then you subtract from that, you subtract from it the initial volume of water. Likewise, for trial number 3, this time we have 3 solid pieces. So for trial number 3, we have solid number 3. So we can measure the mass of solid number 3. So in our graduated cylinder, we'd have 3 of our metal pieces. So then the mass for our trial number 3 would be equal to the mass of solid 1 plus the mass of solid 2 plus the mass of solid 3. The water level would rise even further, so we record the final volume for trial 3. This is part D in the lab manual. This is part D in the lab manual. We're calculating the total mass of the metal pieces and the total volume of the water and metal pieces.
So the volume final is the mass solid 1, 2, and 3 altogether?
The mass total, yes. The final mass.
Oh, okay. So what's the volume final?
The volume final is the final volume, the location of the water level after you've added all of these metal pieces.
Oh, and those are in the pictures?
Yes, exactly. And once you read the volume from your graduated cylinder, you can calculate the volume of all of our solids present for trial number 3 by taking the volume final for trial number 3 and subtracting the initial volume of water. And this initial volume is the initial volume you measured all the way at the start of the experiment. Does that make sense?
So volume initial is just water by itself.
Yes, exactly right.
Okay, got it.
And any change in the water level, any change in the volume is a result of adding this solid.
Okay.
And now, just like before, you have your third data point, which would be the mass of the solid total and the volume of your solid total for trial number 3. And your last data point for trial number 4 would be the mass of the solid total for trial number 4 and the volume of the solid total for trial number 4. So to do that for trial number 4, we're going to have our fourth and final metal piece. We're going to record the mass of our fourth metal piece by difference. And then we're going to have all 4 of our metal pieces in our graduated cylinder. The water level will rise even further, and we're going to record the final volume for trial number 4. The mass for trial number 4 is the total mass of all of our pieces. Further, the volume for trial number 4 so just to recap, we're looking at part D, sections 4 through 7. Yes, you are correct. This collected data will go into this table here. So the volume for trial 4 is just going to be our final volume at the end of trial 4 minus our initial volume. So does this make sense to everyone? How you're going to calculate the mass and volume for each of your 4 trials? Does this make sense to everyone? Any questions on this example? Okay, now I'm going to show you graphing. Now we're going to talk a little bit about graphing. So let's pretend that I've calculated, and I'll show you practically how I've calculated, and we'll do some sample calculations. This will not be due this Sunday, it'll be due next Sunday. So let's suppose for trial 1, I know that the mass of my beaker is 10.0 grams, and the mass of my beaker plus solid is 12.0 grams. My initial volume is 10.0 milliliters. My final volume is 11.0 milliliters. This is just example data. Okay? So from this data, I can find that the mass of my solid is equal to 12.0 minus 10.0 grams, which gives me 2.0 grams. The volume of my solid would be 11.0 minus 10.0, which gives us 1.0 milliliters. So that's the first data set. That's my first data point. So for my mass and volume, for my mass, I have 2.0 grams. For my volume, I have 1.0 milliliters. Does this make sense? How to do this first part of the calculations?
Yes.
Okay, so now for part 2. So I'm just going to draw a picture just to help everyone visualize. For part 1, I just have 1. For part 2, I have 2 metal pieces. So I know that the mass of my beaker is 10.0 grams. The mass of solid number 2 is 11.9 grams. So that in turn gives me a mass of solid 2 as 11.9 minus 10.0 grams, which is 1.9 grams. I then need to calculate the mass of solid total by adding up solid 1 and 2 together. So I get 2.0 plus 1.9, and that gives me 3.9 grams. Does everyone understand why I've calculated the total mass of solid as 3.9 grams. Because I have solid 1 and 2 in my graduated cylinder. Does that make sense? Can I get some responses in the chat, or verbal responses, or a question?
Yes.
Okay, perfect. So that's good. That's really good. This is the critical part of this lab. Now for our volume. So my volume initial is the same as my first trial. It's 10.0 milliliters. And I measure my final volume this time to be 12.1 milliliters. So then the volume of my solids for trial number 2 would be 12.1 minus 10.0, which gives me 2.1 milliliters. Okay, so I have my data from trial 2. From trial 3, let's pretend we're using the same beaker. So the mass of our beaker is 10.0 grams. The mass of our solid is 12.1 grams. So then the mass of our solid from trial 3 is 12.1 grams minus 10.0 grams, which gives us 2.1 grams. Finally, the mass of our solid total is the sum of trial 1, 2, and 3. So I take 2.1 grams from this trial plus 1.9 grams from my previous trial plus 2.0 grams all the way from my first trial. This in turn gives me a total mass of 6.0 grams. Our volume initial stays the same, and this time if our volume final was 13.1 milliliters, we'd say that our volume for our solids for trial 3 would be 3.1 milliliter. Does this make sense?
Yes, so just to recap, the volume initial and volume final, that's going to be given to us.
Yes, and the
Okay.
volume initial will be the same, will be the starting volume of just water before everything was added. And this will be the same for all of the trials.
Gotcha.
Finally, for trial number 4, let's pretend the mass of our beaker was 10.0 grams, and the mass of our solid piece this time that we've added was 12.3 grams. So then the mass of solid number 3 is 12.3 grams minus 10.0 grams. That gives us 2.3 grams. So then the mass of our solid total is the sum of each of our trials. So we have 2.1 grams, 1.9 grams, 2.0 grams, and 2.3 grams. That gives us 8.3 grams. Our V initial again is 10.0 milliliters. And this time, if our volume final was, in this case, 14.3 milliliters, then the volume of our solids would be 14.3 milliliters minus 10.0 milliliters, which would be 4.3 milliliters. Okay, now we're going to tabulate our data of mass versus volume for each of our 3 trials. So for trial 1, the mass was 2.0 grams. and my volume, oops, one moment, and my volume was 1.0 milliliters. For trial 2, my mass was 3.9 and my volume was 2.1. For trial 3, my mass was 6.0 grams and my volume was 3.1 milliliters. For trial 4, my mass was 8.3 grams and my volume was 4.3 milliliters. So now what I'm going to do is I'm going to generate my plot of mass in grams versus volume in milliliters. So we want our graduated marks to be evenly spaced, and we want to have our data occupy the majority of our graph. So I'm going to graph all the way from 0 grams to 10 grams. So first I'm going to divide it into 5 major pieces, and then I'm going to split each of those pieces in half. Okay. And then what I'm going to do is I'm going to split these pieces further into fifths. Okay. So looking at this, so this is just an approximate example here. So each of these little tick marks, let me see here. So this would represent 2, 1, 2, 3, 4, 5, 6. Let me add one more set of tick marks just to make this a little bit more even. Let me adjust these tick marks one more time just to make it a little bit easier to read. I'm just expanding my graph to make it a little bit easier for me to show this. So we have our major tick marks, and then what we're going to do is we're going to add 4 minor tick marks. And the tick marks should be evenly spaced. Okay, so each of these major tick marks represent 1. Each of these minor tick marks represents 0.1 grams. Does that make sense? Does that make sense for the major and minor tick marks? I try to find the common number of tick marks that would allow me to divide up each of my major units and explicitly state my minor units. So in this case, each of your tick marks are 0.2, but in your ideal graph, you'd want each of your minor tick marks to be around 0.1. So as we see, our mass goes from 0 to 10, so we can include all of our data values. Our major tick marks match our major significant figure. Our minor tick marks match our minor significant figure. For our volume, and this will be easier to see, so we'll have it scaled from 1 to 4 milliliters, and we'll divide it hard to do with this pen. We'll do 5. We'll do 5 minor tick marks. So I won't show it for these first few, but we'll do 10 minor tick marks. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have these a little too close. There we go. So from 1 to 2, I have 10 ticks. So each of these little tick marks of the volume represents 0.1 milliliter. Okay, so we have our major ticks representing our major unit, our minor ticks representing our minor significant figure. So we have the mass as a function of volume, and now we're going to plot our data. So my mass is 2.0, so I'm going to find 2.0. My volume is 1.0, so I'm going to put a dot right there. So that's my 0.1. Does that make sense to everyone, how I plotted my first data point? Now we're going to plot our second data point. My mass is 3.9. So I'm going to find around 3.9. My volume is 2.1. So that gives us a data point that is about and let me show with some dotted lines here. So tracing across, that gives us our data point for trial 2. Does everyone see how I traced across to assign my data point? Does this make sense to everyone? Now for trial 3, I have a mass of 6. So let me write out my major units just so that way we can see. And this is technically 10.0, 9.0, 8.0. Okay, so we're going to trace across from a mass of 6 to a volume of 3.1. Oops, not quite there. Okay, so we have our third data point. Let's do our fourth data point now. 4.3 for our volume, 8.3. Okay, so does everyone see how I assigned my data points? Does everyone see how I assigned my data points? So now what I'm going to do is I'm going to try to find a best fit line, a line that encapsulates as many of my data points as possible. It does not need to hit all of my data points. It just needs to get as close to as many of my data points as possible. So this would be an example of a best fit line. This will be an example of a best fit line. Because does everyone notice how my second and third data point, they aren't on the line exactly, but nonetheless, they are still very close to the line. Does that make sense to everyone? Now, Excel will do this for you automatically, and I would encourage you to check your work using Excel, but I do not want you to use Excel for your graph. I want you to make it by hand. Now that we have our graph established, we're going to use a trick. We're going to find data points. We're going to find data points on the graph that are not part of our original data set. And I encourage you to make your life easy. So I'm going to try to find relatively normal values. So I'm going to find this data point and I'm going to read off my X and Y value. So for this data point, for the purpose of calculating slope, I have a volume of 1.5 and a mass of, we're at the second tick, so that would be 3.4. Okay. Let's look at another data point. So these are points from your line that are not part of your original data set. So I see we have a mass of 4. So we have a volume from here of 4.0 milliliters and then a mass of 7.8 grams. Now, if we wanted to calculate the slope, we take the mass 2 minus mass 1 over the volume 2 minus volume 1. So for our mass, we'd take 7.8 minus 3.4 grams. For our volume, we'd take 4.0 grams minus milliliters. We take 4.0 minus 1.0 milliliters. Sorry, 1.5. So that in turn gives us 5.4 grams over 2.5 milliliters. And if we punch that into our calculator, that in turn gives us, for our slope, 2.16 gram per mil, that we round to 2 sig figs of 2.2 gram per mil. Does this make sense to everyone? Does this process make sense to everyone of how we calculated the slope?
Professor, when we are calculating the slope, why we are not using our original data set we already have? Let's pick 2 of those.
Because the data points are representing the data points represent individual parts of your data set. The best fit line is essentially an average fit of your data set. So the best fit line is more representative of your average slope out of all of your data set points. Does that make sense?
Okay, so we always have to find 2 new points.
Yes.
We cannot use our, okay, got it, thank you.
Because the best fit line is essentially averaging all of your data points. Well, it's fitting your data points to an average slope.
Okay.
Yeah. And just to show a comparison, if we were to calculate the density from your data point, for example, 8.3 grams over 4.3 milliliters. Whoops, one moment. That would give us a density of 1.9 gram per mil. If we calculated the density from our third trial, 6.0 over 3.1, that would give us a density of 1.9 gram per mil. So The best fit line that we've drawn, it's not perfect, but it's pretty close if you're using a ruler and if you're really careful picking your points from the line. So you may notice that your average slope may be a little bit different than your best fit line, and that's just because the best fit line when drawn by hand, it may not be perfect. And you can even check your work for your calculated slope using Excel. But I'd like you to practice graphing by hand, as it's a nice skill to develop, as it really helps you see trends in data and notice patterns. Does that make sense to everyone? Does this process make sense? So this is very similar to the graph that you'd make in your own report sheet. And I'll post and I'll save this entire page with all the sample calculations as a reference for you that I'll post on Canvas later today. So, are there any other questions on the laboratory? Are there any other questions on the laboratory today? You'll be taking the data from each of these trials. Notice I have them labeled as trial 1, 2, 3, and 4. From this data, you'll be able to generate a graph and then calculate the slope. After you complete and collect all of your data, you're going to answer questions 1 through 4 in your lab manual. Does that make sense what we're doing today? Does that make sense what we're doing? Any questions? So the plan from here is we're going to spend the remainder of this lab period, working on this lab and reading the pictures. And I'll be available to answer your questions. And I highly encourage you to focus on this lab during the lab time, because I'm here to answer your questions, and the lab is, we've just talked about the lab, so the information is fresh in your mind. So what you'll do is you'll work on this laboratory, you'll complete your report sheets, and this lab will not be due this Sunday, but next Sunday. So I'm going to stop the recording just so that way we have a nice reference that you can watch over for the pre-lab lecture.